A star 700 light-years away is behaving in ways that have never been recorded. Betelgeuse, a red supergiant so massive it would stretch past Jupiter's orbit if dropped in our star's place, violently blew a chunk of its own surface into space. Then it dimmed. Then it surged to its brightest level ever measured. Scientists are watching it around the clock right now, and they are not calm about it. If you enjoy what's coming, subscribe and leave a like. We are going to go from what this star actually is, to what its explosion would do to our sky, to the one signal that would arrive before the light. Prepare yourselves. We begin. Look up on a clear winter night, find the constellation Orion, and shift your eye to the upper left corner. That reddish glow is Betelgeuse. It looks like a quiet dot. It is one of the most extreme objects in our galaxy. Betelgeuse is a red supergiant. That classification alone does not prepare you for the reality of its scale. If you picked up Betelgeuse and placed it exactly where our own star sits, its outer surface would extend past Mercury, past Venus, past Earth, past Mars, and keep going until it swallowed Jupiter's entire orbit. Everything you know as the inner solar system would be inside the star, gone, absorbed. The volume of Betelgeuse is so large that if you hollowed it out, you could fit roughly 700 million stars the size of ours inside it. Picture a single orange in the center of a stadium. The stadium is Betelgeuse. The orange is what we orbit. That comparison is confirmed science, grounded in decades of measurement. And yet, despite that scale, Betelgeuse weighs only about 10 to 20 times more than our star. A red supergiant is enormous because it is bloated, puffed outward by the pressure of nuclear reactions happening deep in its core. The outer layers are thin and extended, more like a vast glowing fog than a solid surface. The star is not dense. It is immense. The surface temperature of Betelgeuse sits around 6,000 degrees Fahrenheit. Our star's surface burns at around 10,000 degrees Fahrenheit. Betelgeuse is cooler, which is precisely why it glows red instead of white or blue. In stellar physics, color is a temperature reading. Red means cool for a star, and cool for something this large means old. Betelgeuse is burning through its fuel at a pace that makes its life brutally short by cosmic standards. Stars like our star live for roughly 10 billion years. Betelgeuse has existed for somewhere between 8 and 10 million years and is already approaching the end. It burned fast because it burned massive. That is the deal every high-mass star makes with physics. Here is something that changes how you hear the rest of this story. The light you see when you look at Betelgeuse left the star roughly 700 years ago. The medieval period on Earth. When that light departed, Betelgeuse was already ancient by stellar standards. What the star looks like right now, in the actual present moment, you will not find out for 7 centuries. That gap between what we see and what is real sits underneath every piece of science we're about to cover. Betelgeuse also pulses. It expands and contracts in slow, rhythmic cycles, like a heartbeat measured in months and years. One of those cycles runs roughly 400 days. Another runs around 5 to 6 years. Scientists have tracked these pulses for well over a century, building a baseline of what normal behavior looks like for this star. That baseline is exactly what made recent events so alarming. The star started doing something outside its recorded patterns. Something that broke the rhythm astronomers had spent generations mapping. And it began with a dimming so severe that it caught the attention of scientists and the public simultaneously. What happened to Betelgeuse starting in late 2019 was so far outside its normal behavior that researchers scrambled to point every available telescope at it. And what they found was stranger than almost anyone predicted. In October of 2019, something changed in the sky above Orion. Betelgeuse began to fade, slowly at first, then faster, dropping in brightness week by week in a way that had no match in modern astronomical records. By February of 2020, the star had dimmed to about 60% of its normal brightness. To the naked eye on a dark night, it was visibly, undeniably different. One of the sky's most recognizable stars was fading. Amateur astronomers noticed first. Then professional observatories confirmed it. Then the question spread beyond research papers and into every news outlet that covered science. Was Betelgeuse about to explode? A supernova is the violent death of a massive star. When a star like Betelgeuse reaches the end of its life, its core collapses in less than a second, and the outer layers rebound in an explosion powerful enough to briefly outshine entire galaxies. Astronomers had long known Betelgeuse was a candidate for this kind of death. Watching it dim so rapidly and so deeply felt, to many, like watching the opening act of something enormous. Social media filled with supernova speculation. Astronomers cautioned patience. The dimming continued. By the time it bottomed out, Betelgeuse had faded more dramatically than at any point in the roughly 150 years of reliable brightness records. Scientists assigned it the lowest measurement in that entire observational history. That record still stands. And then, slowly, it started to recover. The brightness climbed back through the spring and summer of 2020, eventually returning to something close to normal. If this had been a supernova, the star would have blazed, not faded quietly, and then recovered. So the explosion hypothesis faded with the dimming. But that left a harder question open. If Betelgeuse was not dying, what had just happened? A dimming that deep, that fast, with no precedent in the records, required an explanation. And the explanation that scientists eventually landed on was in some ways more unsettling than a supernova prediction. Because what the data revealed was that Betelgeuse had done something to itself. Something active, something violent, something that rewrote what astronomers thought was possible for a living star. The dimming was a symptom. The cause was sitting just beneath the surface of the star, building for years before anyone could see it. And when researchers pieced together what actually happened, they realized they had witnessed an event that had never been observed on any star in recorded history. The Great Dimming was real. The cause behind it was something else entirely. When Betelgeuse started fading in late 2019, the scientific community ran through every explanation on the table. The first possibility was a supernova, dramatic, terminal, civilization-altering. A supernova from Betelgeuse at 700 light-years would be the closest one observed since the year 1604. It would rewrite observational astronomy overnight. The excitement was real, but so was the professional caution. Most experienced astronomers gave it low odds. Stars do not typically dim quietly before they explode. The collapse of a stellar core happens in milliseconds. What was happening to Betelgeuse was slow. The second possibility was a dust cloud. Betelgeuse regularly sheds material from its outer layers. That material can cool and condense into dust, and dust blocks light. If a particularly large clump of freshly formed dust had drifted between Betelgeuse and Earth, it would dim the star from our point of view without anything actually changing on the star itself. This was the leading hypothesis for many months. The third possibility was a temperature drop on the star's surface. Massive stars like Betelgeuse have enormous convection cells moving through their outer layers, similar in principle to the boiling motion in a pot of water, except each cell is the size of a continent or larger. If a particularly cool cell had rotated into prominence on the side facing Earth, it could lower the star's visible brightness. Scientists argued for all three. Teams pointed their instruments at different wavelengths of light, trying to pull the star apart, data point by data point. Ultraviolet observations, radio telescope readings. Each told part of a story, and none of them alone told the whole story. What made it especially difficult was the star's distance. 700 light-years is close by galactic standards, but it is still so far that Betelgeuse appears as a single point of light to most instruments. Resolving detail on its surface requires specialized telescope techniques, and even then the images are blurry disks, not crisp photographs. For months, the dust hypothesis held the most support. It was physically plausible. Betelgeuse was known to shed material. Dust forming in the ejected gas could account for the dimming without requiring anything catastrophic. It felt like a reasonable, even boring answer to what had briefly seemed like a dramatic event. Then the ultraviolet data came in from the Hubble Space Telescope, and the dust hypothesis shifted into something stranger. The ultraviolet readings showed that just before the dimming, there had been an enormous outward movement of material from the star's surface. A surge. Something had pushed material upward and outward with extraordinary force, and then that material had cooled, condensed into dust, and blocked the light. So the dust had a cause, and the cause was violent. Whatever had erupted from the surface of Betelgeuse was large enough to create a dust cloud that dimmed one of the brightest stars in the sky. That raised a new question, one that had never been asked before, about any star. What exactly erupted from the surface? How large was it? And had anything like it ever happened before? The answer to that last question was no. And that made everything that followed much harder to explain. Before the dust formed, before the dimming registered in telescopes around the world, something happened on the surface of Betelgeuse that was almost impossible to explain. A region of the star cooled down dramatically. A localized area on the visible face of Betelgeuse dropped to a temperature far below the surrounding surface. Scientists who study stellar surfaces call this a temperature inhomogeneity. In plain language, one part of the star got cold while everything else stayed hot. And the scale of that cold patch was staggering. The affected area covered a region larger than the distance between Earth and our star. A cold spot on Betelgeuse is not a freckle. It is a continent-sized anomaly on an object already too large to fully comprehend. Temperature maps of stellar surfaces are built from spectroscopic data, meaning scientists decode the light coming from the star and read the temperatures hidden inside different wavelengths. When the cold patch appeared, it stood out immediately in the data. Something was pulling heat away from a huge section of the star's outer atmosphere. The natural first explanation was a giant convection cell. Betelgeuse is known to have convection cells moving through it, massive bubbles of hot plasma rising from deep inside and cooler material sinking back down. Similar to the way heat moves through a lava lamp, but on a scale that defies imagination. A particularly large descending cell of cooler material could produce a visible cold region on the surface. That explanation was clean, familiar, consistent with what was already known about the star's behavior. But the cold patch kept getting colder, and it kept growing. And then the dimming started. As the temperature drop deepened, astronomers tracking Betelgeuse in real time began to suspect they were watching two processes happening simultaneously, which made separating them scientifically very difficult. Was the cold patch causing the dimming by simply radiating less light? Or was the cold patch a sign that material was being pulled upward off the surface, cooling as it rose, before condensing into dust? The connection between the cold spot and the dust cloud above it became the central puzzle of the Great Dimming investigation. Researchers spent months cross-referencing data from multiple telescopes to figure out which event caused the other. The answer they arrived at changed the entire framing of what had happened. The cold patch on the surface was a scar. It was what remained after an enormous amount of material had been violently thrown upward from that exact location. The surface had given up a piece of itself. That realization had no clean precedent in stellar science. Our own star experiences eruptions called coronal mass ejections, where magnetic fields fling plasma outward. Those events are powerful enough to disrupt satellites and power grids on Earth. But what Betelgeuse had done was orders of magnitude larger, and the mechanism appeared to be fundamentally different. The cold patch was evidence of an event so large it left a wound on the surface of a star bigger than the orbit of Jupiter. What had actually been torn away from Betelgeuse was even more difficult to fully absorb. In 2022, a team of astronomers published findings that reframed everything that had happened to Betelgeuse in the previous 2 years. Betelgeuse had not simply dimmed. The star had experienced what scientists named a surface mass ejection, a term borrowed loosely from the smaller phenomenon seen on our own star, but scaled up into something with no real comparison in recorded astrophysics. The star had thrown a piece of its own surface outward into space. Our star produces coronal mass ejections, which are powerful bursts of plasma flung outward by magnetic forces. The largest ones we have measured could fill the distance between Earth and our star several times over and carry the energy of billions of nuclear weapons. They feel catastrophic in scale until you hear what Betelgeuse did. The surface mass ejection from Betelgeuse released somewhere around 400 billion times more mass than the largest coronal mass ejection ever recorded from our star. 400 billion times. Hold that comparison for a moment. If you took the most powerful eruption we have ever measured from our own star and multiplied it by 400 billion, you would begin to approach what Betelgeuse hurled into space during the Great Dimming. The ejected material was not just plasma, it was solid stellar surface. The outer layer of the star, the photosphere, was physically ripped away in one enormous chunk and launched outward. Scientists confirmed this by tracking the movement and composition of the material as it traveled away from the star. It carried the chemical signature of the star's outer atmosphere. It had once been part of Betelgeuse itself. What caused this to happen is still an active area of research. The leading theory, confirmed across several independent studies, involves a pressure pulse originating from inside the star. Betelgeuse generates its pulsing rhythm through internal pressure waves, similar in concept to sound waves moving through a body of gas. Scientists believe one of these internal pressure pulses reached the surface with unusual force, combined with activity in the convective layer just beneath the photosphere. And the result was an eruption from the outside of the star. The physics of that process has no exact parallel in any other observed stellar event. Astronomers had models for how stars shed material gradually. They had models for how magnetic fields could fling plasma outward. They had no model for a star physically throwing away a chunk of its own skin, cooling that material in flight, and turning it into a dust cloud large enough to dim itself from across 700 light-years. After the paper published, the conversation inside the astronomical community shifted. The Great Dimming was solved in the sense that scientists understood what had happened. But understanding what had happened immediately raised a deeper question. If Betelgeuse could do this once, could it do it again? And what does an event like this reveal about where the star actually is in its life cycle? The answers were complicated, because the eruption had left a mark on the star that was still visible, still measurable, and still changing. Numbers in astronomy require translation before they mean anything, so let us work through this carefully. The mass ejected from Betelgeuse during the Great Eruption was estimated to be several times the mass of our Moon. Several lunar masses worth of stellar material ripped from the surface of a star and launched into space in a single event. Our Moon weighs about 730 quintillion tons. Multiplying that by several gives you a mass so large it resists intuitive comparison. But there is one that works. The ejected chunk was heavy enough that if it had been a solid rock, it would have been visible to the naked eye even from a significant fraction of the distance between Earth and our star. The material was not a solid rock, of course. It was superhot plasma, stellar gas laced with heavier elements, moving outward at hundreds of miles per second. As it moved away from Betelgeuse's intense heat, it began to cool. Cooling caused molecules to form. Molecules clumped into tiny solid particles. Those particles were dust. The resulting dust cloud was enormous by any standard applied to space. Astronomers tracked it using infrared telescopes because dust absorbs visible light and re-emits it in the infrared. The cloud's temperature, composition, and movement allowed scientists to calculate backward in time and figure out where it came from and when it was ejected. The cloud was not distributed evenly around the star. It formed primarily on one side, the same side that showed the cold patch on the surface. This directional nature of the ejection confirmed it was a localized event, not a global shedding of the star's outer layers. Something specific happened in one region of Betelgeuse's photosphere, and the material launched outward in roughly that direction. From Earth's position, that side was facing us, which is why we saw the dimming so dramatically. If the ejection had happened on the far side of the star, pointed away, astronomers would have seen very little change in Betelgeuse's apparent brightness. We might have missed the whole thing. That realization introduced an uncomfortable thought. If Betelgeuse had done this before, in past centuries or millennia, and the ejection was pointed away from Earth, we would have no record of it. The Great Dimming might have happened before, several times. We just happened to be in the right position this time to witness it. Scientists have since looked back through historical records of Betelgeuse's brightness and found hints of unusual fluctuations in the past. Whether those fluctuations represent earlier, smaller eruptions or simply normal pulsation variation is still debated. The data is ambiguous, but the possibility that surface mass ejections are a repeating feature of Betelgeuse's behavior has changed how researchers classify the star. Betelgeuse is now understood to be more dynamically violent than previously known. What it did to itself during the Great Dimming left a mark not just on its surface, but on the scientific models built to describe it, and the aftermath of that eruption is still unfolding. The dust cloud formed during the Great Dimming is still out there, drifting outward. Astronomers are still tracking it, and what the star's surface looks like without that missing chunk raises its own set of unsettling questions. Before 2022, stellar physics had a clean vocabulary for how stars shed mass. Stellar winds, gradual outflows of particles streaming away from a star's surface over millions of years. Coronal mass ejections, magnetic field events that fling plasma outward in bursts, powerful but short-lived and ultimately small relative to the star's total mass. Giant eruptions from unstable massive stars in their final centuries of life. Each process had a model. Each model had data behind it. Stellar mass loss was considered a well-understood field. The surface mass ejection from Betelgeuse did not fit any of those categories. It was too large to be a coronal mass ejection. It was too fast and localized to be a stellar wind event. It did not match the gradual shedding expected from a red supergiant in a late evolutionary stage. It was a new category of event, and creating a new category in a mature scientific field is always significant. What makes it matter beyond the astronomy community is what it reveals about how stars behave in the years or centuries before they die. Red supergiants like Betelgeuse are thought to go through increasingly turbulent phases as their cores evolve. The internal structure of the star changes as it burns through successive layers of fuel, from hydrogen to helium to carbon and beyond. Each transition puts new pressures on the outer envelope of the star. Scientists had theoretical models suggesting the outer layers of a pre-supernova red supergiant could become increasingly unstable as the core approached collapse. The Great Eruption appears to be direct observational evidence of that instability. Betelgeuse did not follow the gradual progression the models expected. It threw material off its surface explosively, in a way that required updating those models. Several research groups have since revised their simulations of how red supergiants behave in the centuries or millennia before they explode. The new simulations include the possibility of surface mass ejections as a recurring feature, events that could happen multiple times before the final collapse. If that is correct, the Great Dimming may have been one episode in a series, a sign of a star working itself toward an end that could still be very far away, or disturbingly close. The honest scientific answer is that nobody knows which interpretation is correct. What is confirmed is that the surface mass ejection changed the star. The photosphere, the visible surface, was left with a depression, a region where the material had been ripped away and the surface had not fully reformed. Think of it like peeling skin from a wound. The tissue underneath is exposed. The healing process is visible and measurable if you know what to look for. Astronomers know what to look for, and what they found in the years following the eruption was a star behaving strangely in a new way, its rhythms disrupted, its pulses irregular, its surface still recovering from something it had never been observed doing before. The star's heartbeat had changed, and that shift, quiet and slow as it was, carried implications that went beyond the eruption itself. Every massive star breathes. The breath of a star is not a movement you can see with the naked eye, but it is real and measurable. Betelgeuse expands and contracts in long, slow cycles, driven by processes happening deep inside it. Astronomers call this pulsation, and for Betelgeuse they have been measuring it for well over a century. The pulsation works like this. Pressure builds inside the star as energy generated in the core pushes outward. The outer layers of the star swell in response, expanding outward. But as the layers expand, they cool, and cooling reduces the pressure that drove the expansion. The outer layers then fall back inward, compress, heat up again, build pressure again, and the cycle repeats. On a smaller, denser star, this cycle might happen in days or hours. On Betelgeuse, with its enormous outer envelope stretching hundreds of millions of miles, the cycles take months and years to complete. The star is so large that even a rapid internal change takes an enormous amount of time to propagate to the surface. Betelgeuse has multiple overlapping pulsation cycles. One cycle runs approximately 420 days. Scientists call this the primary cycle, and it is the one driven by the pressure-driven expansion and contraction of the outer layers. A second cycle runs somewhere between 5 and 6 years and reflects a deeper, slower movement inside the star. A third longer cycle lasting around 12 to 17 years has also been identified, though its origin is less clearly understood. These rhythms were stable across the recorded history of Betelgeuse observations. Astronomers could predict the star's brightness months in advance by tracking where it sat in its pulsation cycles. The system was not perfectly predictable, because Betelgeuse is not a simple machine, but the overall patterns were reliable enough to serve as a scientific baseline. After the Great Eruption, that baseline broke. The primary pulsation cycle, the approximately 420-day rhythm, went quiet in a way that had no precedent. The expected brightness peaks failed to arrive on schedule. The cycle's amplitude collapsed. Instead of swelling to its normal brightness highs and dropping to predictable lows, Betelgeuse sat in a kind of muted, uncertain range for an extended period following the eruption. Researchers studying this pattern published findings suggesting the surface mass ejection had physically disrupted the pulsation mechanism. By removing a significant portion of the star's outer layers, the eruption had altered the very surface that participates in the expansion and contraction cycle. The photosphere was thinner in the affected region. The pressure dynamics had changed. The star's own heartbeat was thrown off rhythm by an event it generated itself. That kind of self-disruption had never been documented in any star before. And what scientists found when they tracked the recovery of the pulsation pattern revealed something even more unexpected about where Betelgeuse stands in its life cycle. The rhythm came back, but it came back wrong. By 2023, something became clear in the Betelgeuse data that made astronomers pause at their desks and double-check the numbers. The primary pulsation cycle of Betelgeuse, the approximately 420-day rhythm that had been the star's most reliable drumbeat for over a century of observation, had shifted. The period changed. The timing changed. The pattern that generations of astronomers had used to predict the star's behavior was behaving like a clock that had been dropped and reassembled slightly wrong. The change was confirmed across multiple independent datasets. Teams working in different countries, using different telescopes, cross-referencing different historical archives, all arrived at the same conclusion. The pulsation cycle was not back to normal. It had settled into a new rhythm, measurably different from the pre-eruption baseline. Understanding why this matters requires a brief picture of what the pulsation cycle actually represents. The 420-day rhythm is tied to the physical properties of Betelgeuse's outer envelope: its mass, its temperature, its opacity, meaning how much it resists the flow of radiation through it. The period of pulsation is not arbitrary. It is calculated, effectively, by the star's own physics. If the period changes, it means something about those physical properties changed. The surface mass ejection removed material from the outer layers. Less material means different opacity, different mass distribution, different pressure balance. The eruption rewrote the boundary conditions of the outer envelope, and the pulsation period adjusted to reflect the new physical reality. Astronomers have models for how this should behave as the star recovers. The outer layers should gradually rebuild themselves, accreting material from the surrounding envelope over years or decades. As the surface restores, the pulsation period should creep back toward its original value. That recovery process is currently ongoing, and scientists are tracking it in real time. But the recovery timeline has introduced its own uncertainties. Recovery from an event with no prior observed precedent means there is no comparison set to work from. Researchers are estimating how long the disruption should last, based on theoretical models. And those models were built before the Great Eruption demonstrated that surface mass ejections could happen at all. They are being revised in real time. What the disrupted pulsation cycle cannot tell us, on its own, is whether the star's interior has also been affected. The pulsation changes we observe are surface-level measurements. What is happening in the core of Betelgeuse, where the actual countdown to a potential supernova is governed, remains hidden from direct observation. This is one of the defining frustrations of studying Betelgeuse. The measurements that are most accessible to telescopes are also the furthest from the processes that matter most. Surface pulsation tells you something. It does not tell you everything. What lies inside a red supergiant, and what stage of burning Betelgeuse's core has actually reached, is a question that sits at the center of why scientists are watching this star with such focused, anxious attention right now. To understand what Betelgeuse is doing and where it is headed, you need to go inside it. The interior of a red supergiant is layered like an onion, but an onion made of nuclear fire, each layer burning a different fuel at a different temperature. Each layer piling pressure on the one below it. The process is sequential. When one fuel runs out in the core contracts, heats up to the ignition point of the next fuel, and burning resumes. Each transition is a new chapter in the star's biography. Betelgeuse began its life fusing hydrogen into helium, the same process happening in our star right now. Hydrogen fusion is the longest chapter for any star. For a massive star like Betelgeuse, that chapter lasted only a few million years before the core hydrogen was exhausted. The core then contracted and heated until it reached the temperature needed to fuse helium into carbon and oxygen. Helium fusion runs faster than hydrogen fusion. The chapter is shorter. After helium, carbon. After carbon, neon. After neon, oxygen, silicon. Each stage runs hotter, faster, and shorter than the one before. The timescale compresses dramatically with each transition. The hydrogen burning stage of Betelgeuse lasted millions of years. The silicon burning stage, if it is underway or approaching, lasts on the order of days. At the end of silicon burning, the core fills with iron. Iron is the endpoint of stellar fusion. Fusing iron does not release energy, it requires energy. When an iron core forms, the energy generation that has been holding the core up against gravity for millions of years stops. The core, now dense beyond comprehension, collapses in less than a second. What happens next is a supernova. The core collapse releases an enormous amount of energy, almost all of it carried away by particles called neutrinos. The outer layers of the star, suddenly deprived of the core's support, fall inward and then rebound in a catastrophic shockwave. The star tears itself apart and briefly becomes brighter than the entire galaxy it lives in. For Betelgeuse, this end state is confirmed to be coming. The only question is when, and when depends entirely on what stage the core has reached in its burning sequence. If Betelgeuse is still in the oxygen or neon burning phase, it could remain stable for tens of thousands more years. If it has reached silicon burning, the end could come within years or decades. Scientists have no reliable way to directly observe the nuclear burning stage inside Betelgeuse's core from Earth. What they do have are indirect clues: the surface behavior, the pulsation patterns, the unusual eruptions. Each of those data points carries a faint signal from the processes happening inside, filtered through hundreds of millions of miles of stellar gas. Reading those signals correctly is one of the most consequential scientific challenges of our era, because the answer determines whether Betelgeuse is centuries from death or already lighting the fuse. 700 light-years sounds like it belongs in the category of incomprehensible astronomical distances, and measured against the full scale of the universe, it is close to nothing. But for a supernova, it is close enough to matter in ways that are worth sitting with. A light-year is the distance light travels in 1 year, moving at roughly 670 million miles per hour. In 1 year, light covers about 5.9 trillion miles. Multiply that by 700, and you get the distance to Betelgeuse. The number has so many zeros it becomes meaningless on its own. The comparison that works is this: if the Milky Way galaxy was shrunk to the size of the continental United States, Betelgeuse would be about a quarter inch from where you are standing right now. For a massive star capable of producing a supernova, a quarter inch is extremely close. The closest confirmed supernova in the modern era of astronomy occurred in 1987 in a galaxy called the Large Magellanic Cloud, a small companion galaxy to our own Milky Way, sitting about 160,000 light-years away. That explosion was visible to the naked eye from the southern hemisphere. Astronomers detected a burst of neutrinos from it using underground detectors, which confirmed the core collapse model of supernovae in real time. It was one of the most scientifically significant events of the 20th century. Betelgeuse is about 230 times closer than that 1987 supernova. At 700 light-years, a Betelgeuse supernova would be in a completely different category of observation than anything modern science has recorded. The brightness alone would be transformative. The data available to instruments would be orders of magnitude richer. The neutrino signal would be enormous. The shock wave of stellar material, traveling outward for centuries, would be visible in telescopes as one of the most detailed supernova remnants ever studied. What would it look like from Earth specifically? The numbers have been calculated carefully by multiple research teams, and the answers are striking. At peak brightness, Betelgeuse in supernova would shine roughly as bright as a crescent moon. In daylight, it would be visible as a distinct point of light in the sky, something like a very bright star seen through thin clouds. At night, it would cast faint but real shadows. You could read by it in darkness. It would be bright enough to wake people up if they slept with their curtains open. This level of brightness would persist not for a night, but for weeks, possibly months, before fading over the course of a year or more. And well before the light arrived, there would be another signal. Something faster, stranger, and far harder to detect. Something that would give the scientific community a few hours of warning before Betelgeuse's light changed in the sky. What that warning signal is, and how we have built systems to catch it, is a story that involves particle physics, underground tanks of water, and a race against the speed of light itself. Imagine stepping outside on a clear night and seeing Orion the way you always have: belt, shoulders, the familiar geometry of winter's most recognizable constellation. Then one shoulder blazes. Betelgeuse, the reddish star at the upper left, suddenly burns with a light that overwhelms everything around it. The surrounding stars vanish in comparison. The constellation loses its shape. A single point of fire dominates the sky. That is the opening of a Betelgeuse supernova as seen from Earth. And the scenario is confirmed science, not speculation. The brightness calculations are based on well-understood physics of how supernovae radiate energy, combined with Betelgeuse's known distance and mass. At peak brightness, the event would produce roughly as much visible light as a quarter moon. A quarter moon is enough to navigate by in open terrain. You would see your hand clearly in its light. You would cast a shadow. That light would not flicker or move like moonlight reflected off clouds. It would hold steady, a pinpoint of extraordinary brilliance, sitting exactly where Betelgeuse has always been. The peak brightness would last roughly a week, possibly two. After that, the supernova would begin its long, slow fade, dropping over weeks and months from crescent moon brightness down through star-like levels, eventually dimming below naked eye visibility after roughly a year. During the brightest phase, the event would be visible in full daylight, not as bright as the sky itself, but distinct enough to locate if you knew where to look. Astronomers and casual observers would watch it simultaneously. Entire populations of people who had never thought about a star in their lives would look up. The electromagnetic radiation from the supernova covers more than just visible light. X-rays and ultraviolet radiation would increase as well, though at 700 light-years the levels reaching Earth's surface would be far below any harmful threshold. The planet's atmosphere shields us from those wavelengths. Ground-level effects from a Betelgeuse supernova would be essentially zero in terms of physical danger to living organisms. This is confirmed by multiple independent analyses of the distances involved. What the event would do to human civilization is a different question. The psychological and cultural impact of watching a star die in real time would be profound. Every telescope on the planet, in orbit and on the ground, would swing toward Orion. Scientific papers would flood in. Schools would shift curricula. The event would likely redefine public understanding of what the universe is and what our place in it means. For astronomers, it would be the most scientifically productive event in the history of the field. The quality and quantity of data available from a supernova at 700 light-years, compared to the 160,000 light-year distance of the 1987 event, would be almost incomparable. But before any of that happened, before the light changed a single instrument reading, something else would arrive. Something that travels differently from light. Something that passes through the entire star itself in the seconds of core collapse and races outward ahead of the explosion. A flood of nearly invisible particles that would reach Earth hours before the sky changed at all. When a massive star's core collapses, the event releases more energy in a fraction of a second than our star will radiate across its entire 10 billion year lifetime. Almost none of that energy escapes as light. Almost all of it escapes as neutrinos. Neutrinos are particles so small and so weakly interacting with normal matter that they pass through almost everything. A neutrino can travel through a light year of solid lead without hitting anything. They pass through your body at a rate of tens of trillions per second, produced by our star, and you feel nothing. They are real, they carry energy, and they are extraordinarily difficult to catch. When a stellar core collapses to form a neutron star in the first fraction of a second, the density of the collapsing material briefly becomes so extreme that even neutrinos are temporarily trapped before punching through and escaping. In those few seconds, the core fires a burst of neutrinos so intense it would be one of the most powerful particle events in the universe. At 700 light-years, that neutrino burst would arrive at Earth and wash through the planet, through every person on it, through every building and mountain and ocean, mostly undetected. But not entirely. Physicists built underground detectors specifically to catch neutrinos. These facilities, located deep underground to shield them from cosmic ray interference, consist of enormous tanks filled with ultra-pure water or other materials, surrounded by sensitive light detectors. When a neutrino occasionally interacts with a molecule in the water, it produces a tiny flash of light. The detectors see that flash and record it. Under normal conditions, these detectors catch a handful of neutrinos per day from our star. When a core collapse supernova happens close enough, the detectors are briefly flooded with signals. In 1987, the detectors available at the time caught a burst of roughly 24 neutrinos from the supernova in the Large Magellanic Cloud. That tiny number was enough to confirm the core collapse model and earn a Nobel Prize. A supernova from Betelgeuse would produce a neutrino burst detectable by modern instruments for a duration of about 10 seconds. The current global network of neutrino detectors would register thousands of events in that window. No existing detector could handle the signal without being temporarily saturated. The critical thing is timing. Neutrinos travel at effectively the speed of light, but they escape the star at the very moment of core collapse, before the physical explosion has propagated outward through the stellar envelope. The light from the supernova, which requires the shock wave to actually reach and heat the star's outer layers, takes significantly longer to emerge. The gap between neutrino burst and first light could be anywhere from a few hours to a day or more, depending on the dynamics of the explosion inside the star. That gap is a warning. If the neutrino detectors fire up in a coordinated burst consistent with a nearby core collapse, automated alerts go out within seconds to observatories around the world. Telescopes can be pointing at Orion before the sky changes. The entire first moments of a supernova, never recorded in real time before, could be captured. A system called Supernova Early Warning System already exists and connects neutrino detectors globally for exactly this purpose. It is active, it is watching, and what it is watching for is the signal that Betelgeuse's core has finally given out. You might assume that after decades of precise observation, astronomers would know exactly how old Betelgeuse is and exactly how much longer it has. The answer is more uncomfortable than that. Betelgeuse is genuinely difficult to age. The uncertainty is scientific, real, and unresolved. Stellar age is normally estimated from a combination of mass, luminosity, and composition. You measure how bright the star is and how much it weighs. Then compare that to theoretical models of stellar evolution that predict how a star of that mass and brightness should age over time. For most stars, this process gives a reasonably reliable answer. For Betelgeuse, nearly every input into that calculation carries unusual uncertainty. The mass of Betelgeuse is estimated at somewhere between 10 and 20 times the mass of our star. That is a wide range. The difference between 10 solar masses and 20 solar masses at the high end changes the predicted lifetime dramatically. A more massive star burns faster and dies younger. A less massive star burns slower and could live longer. The uncertainty in Betelgeuse's mass alone means its age estimate spans millions of years in either direction. The distance measurement introduces further complications. Betelgeuse is close enough that astronomers can measure its angular size, meaning they can see it as a tiny disk rather than a true point of light. Knowing the angular size and the distance allows a calculation of the physical size, which feeds back into estimates of luminosity and mass. But the distance measurements themselves have been revised multiple times as better instruments have been deployed. As recently as 2020, a revised distance calculation shifted the estimated value by a significant margin, which cascaded into revised mass and luminosity estimates. On top of all this, Betelgeuse has mass-losing events in its history that complicate the picture further. If the star ejected a significant amount of material through surface mass ejections or stellar winds over its lifetime, its current mass is lower than its birth mass. How much lower depends on the full ejection history, which is incompletely known. The result of all these compounding uncertainties is that estimates for Betelgeuse's remaining lifetime range from tens of thousands of years to less than 100,000 years. Some models place the supernova within a human timescale. Others push it to a geological timescale. A few researchers argue the eruption patterns suggest the star is in a pre-collapse turbulent phase that historically precedes a supernova by a relatively short window. None of these are fringe positions. They are all grounded in published science, using the same observational data, interpreted through models that each have legitimate support. The honest scientific status of Betelgeuse's timeline is that it is unknown. And that uncertainty is exactly what makes the next observation so important. Because in one of the stranger implications of stellar physics, the star may have already made the decision without us knowing. Here is the thought that sits quietly behind every paper written about Betelgeuse. The light you see from Betelgeuse when you look toward Orion tonight left that star roughly 700 years ago. Everything we know about the star, every measurement of its pulsation, every analysis of its eruption, every calculation of its remaining lifetime, is built from information that is 7 centuries old by the time it reaches our instruments. The actual, present-day Betelgeuse, the star as it exists in the universe right now at this moment, is unknowable to us. We cannot see it. We cannot measure it. We are watching a recording, and the recording is 700 years out of date. This is not a philosophical point. It is a confirmed physical reality of how light travels through space. The information we receive from any distant object is always historical by a time equal to the light travel time from that object to Earth. For Betelgeuse at 700 light-years, that delay is 700 years, which means Betelgeuse could have gone supernova at any point in the last 700 years, and we would have no record of it yet. If the core collapsed in the year 1500, the light from that explosion will arrive here in the 2200s. If it collapsed 50 years ago, the light arrives 650 years from now. If it collapsed yesterday, in the actual present, the light begins its 700-year journey toward us right now. At some point, if Betelgeuse does go supernova, the arriving light will hit Earth's atmosphere and the sky will change. There will be no warning beyond the neutrino burst arriving hours ahead. One night Betelgeuse will be the familiar reddish star, and then it will not be. The only true constraint is that we know Betelgeuse had not yet exploded 700 years ago, because we are still receiving its normal starlight. The star was alive in the medieval period. Everything after that is unknown. Astronomers use careful phrasing around this point. They say Betelgeuse will explode within the next 100,000 years, accounting for the light travel time, meaning the explosion event itself could occur anywhere in a window from 700 years in the past to 100,000 years in the future. The light from any event in that range has either already departed and is traveling toward us, or has yet to depart. This is one of the places where the strangeness of cosmological distance becomes genuinely difficult to process. We are watching a star that may already be dead. Every image ever taken of Betelgeuse, every brightness measurement, every pulsation recorded, could be a photograph of something that no longer exists. What we would see in the moment of its death is not the star dying. It is the news of its death finally arriving. And what that news looks like, what it reveals about the star's interior in the moment of collapse, is something astronomers have been preparing to document for decades. When astronomers first managed to directly image the surface of Betelgeuse, they expected something roughly spherical, a massive ball of hot gas, enormous and bright, but fundamentally round the way planets and stars are supposed to be round. The surface they saw was lopsided. Betelgeuse is asymmetrical in ways that go well beyond surface texture. The star is not uniformly round. Certain regions of its surface are dramatically brighter and hotter than others. The outer atmosphere extends unevenly in different directions. Enormous structures, Hot, bright regions covering areas larger than the entire distance between Earth and our star move across the surface in patterns that do not follow simple rotational symmetry. What creates this asymmetry are convective cells. Inside Betelgeuse, hot material rises from deep within the star, pushes outward, reaches the surface, and spreads. Cooler material sinks back down. This convective motion is the same fundamental process that happens in our star, but in Betelgeuse, the scale is almost absurd by comparison. A typical convective cell in our star is roughly the size of Texas. A typical convective cell in Betelgeuse is roughly the size of the distance between Earth and our star, about 93 million miles across. These cells are so large that only a handful fit inside the star at any given time, sometimes as few as 2 or 3. When you have only 2 or 3 enormous cells churning on a star's surface, the result is visible asymmetry. One side is hotter and brighter because a rising cell is positioned there. Another side is cooler and dimmer because a descending cell dominates. These cells are not static. They shift over timescales of months to years, slowly rotating and reforming as new material rises and old material sinks. The star's appearance changes as the cells move. Parts of Betelgeuse that were bright last year may be dimmer this year, and vice versa. This convective activity is almost certainly connected to the Great Eruption. The leading models of how the surface mass ejection occurred involve a particularly energetic convective upwelling reaching the photosphere, with unusual force, driving material off the surface from below. The lopsided nature of Betelgeuse's convection means these events are inherently directional. The eruption came from one spot, because that is where the convective energy concentrated at that moment. The asymmetry also makes predictions about Betelgeuse's behavior more difficult. A symmetric star with smooth, predictable behavior is easier to model. A star with giant irregular convection cells that periodically erupt pieces of its surface requires far more complex simulations. The models exist, but they carry wider error bars. One thing the asymmetry tells us with confidence is that Betelgeuse's surface is alive in a way that most objects in the universe are not. It is dynamic, changing, violent on timescales humans can observe within a lifetime. But what the star's surface is made of, what fills its outer atmosphere, and what the chemistry of the material it sheds into space actually contains, is a story with details that are almost impossible to expect. The outer atmosphere of Betelgeuse is not empty space with a hot star sitting in the middle of it. It is a chemical environment unlike anything in our immediate solar neighborhood. The region surrounding Betelgeuse, extending outward for hundreds of times the distance from Earth to our star, is filled with a complex mixture of molecules, atoms, and dust grains that have been shed from the star over millions of years. Red supergiants are cool enough at their surfaces, relative to hotter stellar types, that molecules can form in their atmospheres. Our star is too hot for this. Its outer layers are so energetically intense that molecules get torn apart the instant they try to form. Betelgeuse, with its cooler surface temperature, allows molecules to survive. The result is a chemically rich outer envelope that astronomers can probe using radio telescopes. Scientists have detected dozens of different molecular species in Betelgeuse's extended atmosphere. Water molecules exist out there, despite the star's intense radiation environment, because the outer layers are cool enough to allow their survival. Silicon monoxide exists in the inner atmosphere, formed from silicon atoms shed off the star's surface. Further out, where temperatures drop lower as you move away from the star's heat, more complex molecules form. Carbon-bearing molecules. Molecules that contain sulfur. Molecules that in a different context would be classified as the building blocks of organic chemistry. The dust that forms in Betelgeuse's outer envelope is made primarily of silicate grains, tiny particles with compositions similar to sand, and aluminum oxide particles. These grains are a few millionths of an inch in size. They form as the ejected gas cools below certain temperature thresholds. The same basic physics that produced the dust cloud during the Great Dimming. This dust is not unique to Betelgeuse. Red supergiants are among the primary producers of dust in the galaxy. The material they shed over their lifetimes, and especially in the supernova explosion that ends them, contributes enormous amounts of solid particles to the interstellar medium the sparse material that fills the space between stars. That material eventually gets swept up into new clouds of gas and dust. Those clouds collapse to form new stars and planetary systems. Some fraction of the material in the ground beneath your feet was processed through a star like Betelgeuse, before finding its way into the cloud that eventually formed our solar system. The silicon, the carbon, the heavier elements in the rocks and soil and in your bones, came through systems like this one. Betelgeuse is not just a spectacle, it is a factory, and the galaxy runs on its output. What the star has already shed into the surrounding space, and what it will release in its eventual supernova, will become raw material for stars and planets that do not yet exist. The chemistry inside Betelgeuse's atmosphere is, in a real sense, the chemistry of the future. And that future becomes much more immediate when you consider what ancient records suggest about how fast this star is changing, and how different it may have looked to people who studied the sky long before our telescopes existed. Ancient sky watchers were careful people. They tracked the stars across decades and centuries, passing records from generation to generation, building catalogues of stellar positions and colors that modern astronomers still reference. These were not casual observers, they were professionals in every meaningful sense, paid by courts and temples to map the heavens with precision. Several of those records describe Betelgeuse as yellow. The astronomer Ptolemy, working in the 2nd century, classified Betelgeuse alongside other yellow and orange stars in his catalogue. 1,000 years later, the medieval Islamic astronomer Al-Sufi produced detailed star charts and assigned Betelgeuse a color description consistent with an orange or reddish-yellow tone, meaningfully different from the deep red we observe today. This matters enormously. Stellar color is tied directly to surface temperature. A yellow star runs hotter than a red one. If ancient records are accurately describing Betelgeuse as yellower than it appears today, the star may have cooled significantly over the past 2,000 years. And a star cooling that fast, dropping from yellow to red across 2 millennia, would be evolving at a pace that is, by astronomical standards, almost shockingly rapid. The controversy around this interpretation is real and ongoing. Some researchers argue the ancient color descriptions reflect the language and perceptual conventions of different cultures, rather than precise colorimetric measurements. Color vocabulary in ancient languages does not map cleanly onto modern spectral classifications. What one culture called yellow, another might describe as reddish gold. The linguistic ambiguity is genuine. Other researchers take the records more literally and argue the color shift is real. A star that has visibly changed color in 2,000 years would be a star undergoing observable evolution within a human historical window. That kind of change would push Betelgeuse's active evolutionary timeline much closer to our present than the geological timescales some models predict. The scientific community has not resolved this debate. Both positions have published support. Both have legitimate objections. What the ancient records do establish beyond doubt is that Betelgeuse has been a prominent object of human attention for at least 2,000 years, and that its behavior across that window has varied enough to generate disagreement about its basic appearance. A star that sparks arguments about what color it is across 2 millennia of observation is not a stable, boring object. It is a star that changes, and a star that changes visibly on human timescales is a star demanding attention. The color question also connects to a deeper mystery about Betelgeuse's pulsation history. If the star was genuinely hotter in the past and has been cooling across centuries, that trend may reflect an ongoing evolution in its internal burning stages, a slow shift in the star's energy output as its core works through successive fuel layers. If that interpretation is correct, the great dimming and the disrupted pulsation cycles are not isolated events. They are the latest chapters in a slow change that has been underway for centuries, visible to anyone who knew how to look and had the records to compare. The dust cloud from the Great Eruption, still drifting outward right now, is the most recent piece of that ongoing story, and astronomers are watching it move in real time. Chapter 19: The Dust Cloud Aftermath. The material Betelgeuse ejected during the Great Eruption did not disappear. It is still out there. After the surface mass ejection, the enormous chunk of stellar material traveled outward away from the star, cooling as it moved through the progressively colder region beyond the photosphere. As the temperature dropped below certain thresholds, The gas began to condense into solid particles. Silicate grains formed. Aluminum oxide particles formed. A true dust cloud assembled itself in real time, extending across a region hundreds of millions of miles wide. Astronomers detected this cloud using infrared telescopes because dust at those temperatures radiates strongly in infrared wavelengths while absorbing visible light. The cloud's infrared signature was distinct enough to map its rough shape, estimate its total mass, and calculate the velocity at which it was moving away from the star. Based on those measurements, the cloud was moving at roughly a few miles per second relative to Betelgeuse. At that speed, it would take thousands of years to travel the distance between Earth and our star. It is not heading toward us in any meaningful sense. The cloud is expanding outward in the direction it was initially launched, spreading and thinning as it disperses into the surrounding space. What makes tracking this cloud scientifically valuable is what it reveals about the ejection mechanics. The cloud is not perfectly uniform. It has denser regions and thinner regions, reflecting the structure of the material as it was launched and the way it cooled unevenly. The denser clumps correspond to areas where the ejected material was most concentrated when it left the surface. Researchers comparing the cloud's current structure with the cold patch that appeared on Betelgeuse's surface during the Great Dimming found strong spatial correspondence between the densest clump of the cloud and the location of the cold patch. The material came from that specific region of the photosphere. The scar on the surface and the cloud in space are directly connected, cause and effect separated now by millions of miles of vacuum. The cloud is also fading in infrared brightness as it cools. The dust grains are slowly dropping in temperature as they move further from the star's radiation. Tracking the fading rate allows scientists to refine estimates of the cloud's total dust mass and grain composition, information that improves models of how red supergiants in general shed material throughout their lives. One striking aspect of this observation is how directly it connects to galactic chemistry. The dust now dispersing from Betelgeuse will eventually spread into the surrounding interstellar medium. Over millions and billions of years, it will contribute to the raw material of future star systems. Astronomers are watching in real time the process by which a star seeds space with the building blocks of future worlds. The cloud will outlast any human civilization currently imaginable. Long after Betelgeuse itself has exploded or faded from the sky, the material it shed in 2019 and 2020 will still be drifting, spreading, and slowly becoming part of the galaxy's wider chemistry. But what is happening closer to the star right now, deep inside its core, is the process that determines everything. And the specific element produced at the end of that process carries a significance that goes beyond chemistry. Chapter 20. What iron in a stellar core means. Every fuel that burns inside a massive star releases energy. Every step in the fusion chain, from hydrogen through helium, carbon, neon, oxygen, and silicon, produces energy because the products are lighter than the ingredients. The mass difference converts into energy. That energy is what holds the star up against the crushing inward pull of its own gravity. Iron breaks that chain. When a stellar core fuses silicon into iron, nothing useful comes out. Fusing iron does not release energy. It absorbs energy. The core has spent its entire life generating outward pressure to balance gravity, and the moment the iron accumulates faster than it can be dealt with, that balance collapses. The iron core grows. Fusion at its edges keeps adding iron to the pile. The core gets heavier and denser and hotter. It cannot fuse its way out of the problem. It cannot generate any more energy to push back against the weight of the entire star pressing down on it. When the iron core reaches a mass roughly 1.5 times the mass of our star, it crosses a threshold. Electrons, which had been providing some resistance to compression through quantum mechanical pressure, can no longer hold their positions. They are forced into the protons of atomic nuclei, creating neutrons and releasing neutrinos. The core, suddenly stripped of its electron pressure, falls inward. In less than 1 second, a core roughly the size of Earth collapses to a ball roughly 12 miles across. The densities involved are beyond any material comparison. A teaspoon of the resulting neutron star material would weigh about 10 billion tons. The collapse releases an amount of energy that staggers any attempt at description. In that fraction of a second, The energy output exceeds what our star will produce across its entire 10 billion year lifespan by a factor of roughly 10 billion. Nearly all of that energy escapes as neutrinos. The neutrino burst is the first signal that the star has died. The outer layers of the star, still falling inward when the core collapse bounces, slam into the newly formed dense core and rebound in a shockwave moving outward at tens of thousands of miles per second. The shockwave tears through the star's outer layers, heating them to extreme temperatures and triggering additional fusion of heavy elements. Elements heavier than iron, including gold, silver, and uranium, form in the chaos of the expanding shockwave. Betelgeuse is not just a dying star. In its final moments, it becomes a factory for the heaviest atoms in the periodic table. This entire sequence, from the formation of the iron core to the shockwave reaching the stellar surface, takes roughly a day. Then the light begins. Whether Betelgeuse's core has started this final sequence, whether iron is accumulating somewhere deep inside the star right now, is a question with no definitive answer. The core is hidden behind hundreds of millions of miles of stellar gas. Direct observation is impossible with current technology. What scientists do have are the theoretical timelines, the models of stellar evolution, and the surface behavior of the star itself as indirect evidence. Those models do not agree on the timeline, and the disagreement among experts is sharper than most public reporting suggests. Chapter 21: The competing theories about what triggers the final collapse. When researchers who study massive stellar evolution sit in the same room, they do not reach consensus on Betelgeuse's timeline. The debate is active, technical, and genuinely unresolved. The core disagreement centers on what internal stage Betelgeuse has reached and how the star's surface behavior maps onto those internal processes. One group of scientists argues that Betelgeuse is in an advanced burning stage, potentially oxygen or silicon burning, and that the surface instability observed over recent years is consistent with the kind of turbulence models predict for a star in the late stages before collapse. These researchers point to the Great Eruption, the disrupted pulsation cycle, and the historical brightness changes as evidence of a star whose interior is evolving rapidly. Their models place the supernova within a window that, while still uncertain, could fall within tens of thousands of years at the far end and within a human lifetime at the near end. The other group argues that the surface events are explained fully by the hydrodynamics of the outer envelope and carry no reliable information about the burning stage of the core. They point out that surface mass ejections, pulsation disruptions, and brightness variations can arise from mechanisms in the outer layers of the star without any change in the core's burning status. A red supergiant's outer envelope is turbulent and complex, and attributing surface chaos to core evolution requires assumptions that the data does not firmly support. Their models place Betelgeuse potentially hundreds of thousands of years from collapse. Between those positions sits a wide range of intermediate views, each grounded in different assumptions about stellar mass, convective behavior, and the reliability of surface pulsation as a probe of interior conditions. What both sides agree on is that the current models of red supergiant evolution are incomplete. Before the Great Eruption was identified and characterized, no stellar model included surface mass ejections as a feature. Those models are now being revised, which means the simulations that form the basis for timeline predictions are actively changing. New data feeds into new models, feeds into revised estimates, and the cycle is ongoing. One specific theoretical framework gaining traction involves the idea that the pulsation behavior of a red supergiant in its final evolutionary stages becomes increasingly erratic due to the changing pressure structure in the core. As the core burns through successive fuels, the energy output changes in ways that ripple outward into the pulsation dynamics of the outer layers. If this framework is correct, the disrupted 400-day cycle is a genuine signal from the core rather than a surface artifact. That framework would put Betelgeuse's erratic behavior in a new context. The great dimming, the record brightness surge that followed it, the broken pulsation, the great eruption itself, could be understood as a sequence of escalating signals from a star whose interior is entering its final chapters. The framework is published and peer-reviewed. It is contested by other peer-reviewed work. Astronomy does not have a verdict yet. What is certain is that whatever the timeline, when Betelgeuse finally goes, the explosion will distribute matter across an enormous volume of space. And that matter carries a significance that extends beyond the star itself. Chapter 22: How Supernovae Seed Life. The elements inside Betelgeuse are not staying there forever. When the star eventually explodes, everything it has accumulated over millions of years of fusion, along with the heavier elements forged in the explosion itself, will be scattered across a volume of space hundreds of light years across. The shockwave will carry stellar material outward at a significant fraction of the speed of light, eventually slowing as it sweeps up the surrounding interstellar gas, forming a glowing shell called a supernova remnant. That remnant will expand for tens of thousands of years. The material inside it, seeded with carbon, oxygen, silicon, iron, and traces of every element heavier than hydrogen and helium, will gradually mix into the wider interstellar medium. Clouds of gas enriched with this stellar material will eventually become gravitationally unstable and collapse. New stars will form inside them, and around those new stars, the planets that form will be built partly from the atoms that once burned inside Betelgeuse. This process is confirmed science. Every rocky planet we know of, including Earth, formed from material that was previously inside one or more stars that exploded before our solar system existed. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was forged in stellar cores and distributed by supernovae over the roughly 9 billion years of cosmic history that preceded the formation of our solar system. Betelgeuse is one link in a chain that has been running since the first massive stars formed roughly a few 100 million years after the universe began. Those first stars, massive and fast-burning, seeded the early universe with the first heavy elements. Later generations of stars built on that foundation, producing heavier and more complex atoms. Each generation of stellar death made the next generation of planets and life more chemically possible. The supernova remnant that Betelgeuse produces will be observable for thousands of years. Some of the most studied objects in the sky are supernova remnants from relatively recent explosions in recorded human history. The Crab Nebula, for example, is the remnant of a supernova observed by Chinese astronomers in the year 1054. After nearly 1,000 years, it is still expanding, still glowing, still actively studied. It spans roughly 11 light-years across today. A Betelgeuse remnant would begin with far more energy and mass. It would expand into the surrounding space that Betelgeuse has already been enriching with stellar winds for millions of years. The interaction between the explosion shockwave and that pre-existing material would create complex structures, filaments, and shells and bow shocks, visible to telescopes for tens of thousands of years. What sits at the center of that future remnant is itself uncertain. The nature of the compact object left behind after a supernova depends critically on the mass of the collapsing core, and for Betelgeuse, even that is genuinely unknown. Chapter 23: The Betelgeuse Nebula that will form. Within hours of core collapse, Betelgeuse's outer layers will be moving outward at tens of thousands of miles per second. The initial explosion will be violent enough to be called a catastrophic failure of the star's structural integrity. Everything above the collapsing core gets launched. The outer atmosphere, the convective envelope, the photosphere, the dust and gas clouds surrounding the star, all of it gets caught in the expanding shockwave and driven outward. The star ceases to exist as a coherent object within roughly a day. What follows is a long, slow process of material spreading through space. In the first days and weeks, the expanding material glows intensely as it catches and re-emits the enormous energy of the explosion. This is the visible supernova, the event that lights up the sky. The surface of the expanding shell heats to extreme temperatures and radiates across a broad spectrum, from radio waves through X-rays. As weeks become months and the shell expands and cools, the visible brightness fades, but the structure continues to develop. The material is moving at different speeds depending on what layer of the star it came from. Inner layers, driven by the initial shockwave, move faster. Outer layers, which were already moving slowly in the stellar wind before the explosion, get swept up by the faster inner material. This creates complex collisions within the expanding remnant, generating X-ray emission and turbulent filamentary structures. Within a few thousand years, the remnant has expanded to cover a region tens of light years across. Its outer edge is a shockwave sweeping up the surrounding interstellar medium, compressing it and heating it to millions of degrees. Astronomers call this the supernova remnant shock front, and it glows in X-ray wavelengths long after the visible light has faded. The region around Betelgeuse already contains significant amounts of material shed by the star over millions of years of stellar winds and eruptions. The supernova shockwave will interact with all of that material, creating an unusually complex remnant structure. The dust cloud from the great eruption of 2019, still drifting outward from the star, will eventually be overtaken by the explosion shockwave and get swept into the remnant. In tens of thousands of years, the remnant will have expanded enough to begin merging with the surrounding interstellar medium, enriching it with the chemical products of Betelgeuse's life and death. Future astronomers, in whatever civilization exists to study the sky at that point, would see a large, complex glowing cloud in the region of Orion, a fossil record of one of the closest supernovae in human history. At the geometric center of that cloud, or somewhere within it, there would be a compact object, a dense, spinning remnant of the collapsed core. Whether that object would be a neutron star, the most extreme stable form of matter known to science, or a black hole, depends on a number that scientists are currently debating. Chapter 24. Whether a neutron star or black hole forms. The core of Betelgeuse will collapse. What it becomes after that collapse depends on how much mass is left over after the explosion, and that number is genuinely uncertain. If the collapsing core ends up with a mass below roughly 2 to 3 times the mass of our star, the collapse stabilizes. The density becomes so extreme that the neutrons themselves, packed together as tightly as the laws of physics allow, provide enough pressure to halt the collapse. The result is a neutron star, a ball roughly 12 miles across, containing the mass of a star, spinning rapidly and radiating energy across a broad spectrum. Neutron stars can spin hundreds of times per second and emit beams of radiation that sweep the sky like a lighthouse. When those beams sweep across Earth, we call the object a pulsar. If the collapsing core ends up above that mass threshold, the neutron pressure is insufficient. Gravity wins completely. The collapse continues without limit, and a black hole forms. No signal escapes from the core. The explosion still happens in the outer layers, but the central object disappears behind an event horizon. For Betelgeuse, the outcome is genuinely uncertain, because the total mass of the star carries wide error bars, and the amount of mass ejected in the explosion also varies depending on the explosion's energy and mechanics. Both of those factors feed into the final core mass calculation, and both are imprecisely known. Current estimates put Betelgeuse in a range where either outcome is plausible. Stars with initial masses between roughly 15 and 20 times the mass of our star sit near the boundary between neutron star and black hole formation, and Betelgeuse's estimated mass falls in that range. Some explosion simulations favor a neutron star. Others, particularly those modeling higher initial mass scenarios, produce a black hole. A failed supernova is another possibility that some researchers have raised. In this scenario, the explosion is not powerful enough to expel the outer layers, and most of the star's mass falls back onto the neutron star, pushing it over the mass limit and forming a black hole. From a distance, a failed supernova would look like a star simply disappearing, brightening briefly and then vanishing, rather than producing the extended brilliant display of a conventional supernova. Astronomers have observed a handful of candidate failed supernova in other galaxies. Whether Betelgeuse would produce a canonical supernova or a failed one is another open question in the literature. The probability assessment varies depending on the mass estimate used as the starting point. What makes this particular uncertainty more pressing than a purely academic question is a separate risk that comes specifically from massive star collapses, a risk that depends on the geometry of the collapse and on whether Betelgeuse is, in a very specific sense, pointed at us. Chapter 25. The Gamma-ray burst risk. Some massive star supernovae produce something in addition to the standard explosion. A focused beam of extraordinarily intense radiation, called a gamma-ray burst, fired from the collapsing core along the star's rotational axis. Gamma-ray bursts are the most energetic electromagnetic events known in the universe. A single burst can release more energy in a few seconds than our star will emit across its entire lifetime. At cosmological distances, the ones we detect from billions of light years away, they represent no hazard to Earth. The energy disperses over such vast distances that by the time it reaches us, it is measurable but not dangerous. At 700 light-years, the calculation changes. If Betelgeuse were to produce a long gamma-ray burst, a type associated with the collapse of rapidly rotating massive stars, and if the jet from that burst were aimed in Earth's direction, the energy arriving at our atmosphere would be significant. Estimates from multiple research papers suggest a gamma-ray burst from Betelgeuse, if aimed at Earth, could deliver enough high-energy radiation to partially deplete the ozone layer over a wide area. Ozone depletion at the scale some models suggest would increase ultraviolet radiation reaching the surface for years, affecting ecosystems and agricultural systems. There is an important set of conditions surrounding this scenario. Long gamma-ray bursts require a rapidly rotating stellar core. The star's core must be spinning fast enough that the collapse produces focused jets rather than a roughly symmetric explosion. Betelgeuse rotates slowly relative to the stars that are most commonly associated with gamma-ray burst production. A team of astronomers studying Betelgeuse's rotation rate published findings suggesting it is likely too slow to produce the focused jets required for a long gamma-ray burst. That conclusion is considered the scientific consensus position. The risk of a gamma-ray burst from Betelgeuse is assessed as low to negligible by most researchers in the field. The slow rotation is the key disqualifying factor. The secondary question is whether the star's rotational axis is aimed anywhere near Earth, even in theory. Measurements of Betelgeuse's rotation suggest its axis is tilted such that the poles, where jets would emerge, are not directed toward our solar system. A combination of slow rotation and unfavorable geometry significantly reduces the already low probability. The gamma-ray burst scenario for Betelgeuse is published, examined, stress-tested against the available data, and largely dismissed by the scientific community as a meaningful hazard. The supernova itself, the light in the neutrinos and the shockwave, carries no danger to Earth at this distance. The honest conclusion is that a Betelgeuse supernova would be a spectacular scientific event and a profound cultural experience, with no meaningful physical threat to life on this planet. The star that poses more unsettling questions about what extreme stellar instability actually looks like is not Betelgeuse at all. It is a different neighbor, further away but far more chaotic. Chapter 26: How Betelgeuse Compares to Eta Carinae. If Betelgeuse makes astronomers anxious, Eta Carinae makes them quietly terrified. Eta Carinae is a star system sitting about 7,500 light-years away, roughly 10 times further than Betelgeuse. Inside that system is a star, or possibly two stars locked in an extraordinarily tight orbit, with a combined luminosity estimated at roughly 5 million times the output of our star. Betelgeuse, enormous as it is, outputs roughly 100,000 times our star's luminosity. Eta Carinae outpaces it by a factor of 50. Stars that luminous are called hypergiant or luminous blue variable stars. They sit at the absolute edge of what physics allows a star to be without simply blowing itself apart. The radiation pressure from a star this bright is so intense it pushes on the star's own outer layers with a force approaching the inward pull of gravity. The star is perpetually on the edge of shedding itself. In the year 1843, Eta Carinae did something remarkable. It brightened dramatically, becoming the second brightest star in the sky for a period, then faded back. This event, called the Great Eruption of Eta Carinae, ejected a mass equivalent to roughly 10 times the mass of our star into the surrounding space. That ejected material forms a distinctive double-lobed nebula surrounding the star today, called the Homunculus Nebula, still visible and still expanding. The lobes span roughly 1 light-year across and are among the most studied structures in the southern sky. The mechanics of the 1843 eruption are still debated. A true supernova was expected to destroy the star, but Eta Carinae survived. The event was so energetic it should have been terminal by standard models, yet the star persisted. Some researchers classify the event as a supernova imposter, a near-death experience that mimics a supernova without actually completing the core collapse. Others invoke binary star interaction as the driver, with the companion star triggering the eruption rather than internal instability alone. What connects Eta Carinae to Betelgeuse is the broader question both stars raise about pre-supernova behavior. If a star can undergo eruptions of that scale and survive, even temporarily, what does pre-supernova instability actually look like? How violent can the symptoms get before the final collapse? Both stars push against the boundaries of models that were built assuming more gradual, predictable behavior. Eta Carinae, at 7,500 light-years, is more distant than Betelgeuse, but its mass and luminosity are so extreme that a supernova from that system could potentially produce effects more significant than a Betelgeuse event, despite the greater distance. Some calculations suggest Eta Carinae's gamma-ray burst risk, given its higher mass and suspected faster rotation, is more worthy of examination than Betelgeuse's. Both stars are being monitored. Both carry their own scientific anxieties. But between them, Betelgeuse holds the distinction of being the one whose surface has been directly imaged in extraordinary detail, something that changed what astronomers believed was possible in stellar observation. Chapter 27. The Hubble Images That Changed Everything. For most of astronomical history, stars were points of light. Even through the largest ground-based telescopes, the angular size of stars other than our own was too small to resolve into any meaningful disk. Astronomers measured brightness, color, and spectrum, but the surface of a distant star was inaccessible. It remained a theoretical object described by physics rather than a place that could be seen. That changed for Betelgeuse in 1996, when the Hubble Space Telescope captured the first direct image of the surface of a star other than our own. The image was not sharp by photographic standards. Betelgeuse resolved into a small, blurry orange disk, crossed by a brighter region in one area of the surface. By the standards of conventional photography, it would not seem impressive, but in the context of what was known and what had been possible before, the image was transformative. For the first time, astronomers were looking at the actual surface of another star. The brighter region visible in that image was a hotspot on the photosphere, a feature consistent with an enormous convective cell pushing hot material upward. The asymmetry of the disk confirmed what theory had suggested, but never directly demonstrated. Betelgeuse's surface was not uniform, not smooth, not symmetric. Subsequent imaging campaigns using Hubble and other high-resolution instruments built on that first image. Techniques that combine the light from multiple telescopes to achieve higher resolution, called interferometry, allowed astronomers to produce increasingly detailed maps of Betelgeuse's surface over the following decades. Bright regions tracked across the disk over months, corresponding to the movement of giant convective cells. The star's size appeared to fluctuate slightly with its pulsation cycle. The outer atmosphere extended unevenly in different directions. In 2019, just before the Great Dimming began, Hubble captured ultraviolet images showing an unusually dense and bright region in the star's ultraviolet chromosphere above the southern hemisphere of the star. This concentration of material was later connected to the sequence of events that produced the Great Eruption. The Hubble data, in retrospect, captured a precursor signal of the eruption before it happened. The ability to directly image Betelgeuse's surface has made it a uniquely valuable laboratory for stellar physics. Every major theoretical prediction about how red supergiants behave, from convection patterns to mass loss to pulsation mechanics, can be tested against actual surface observations rather than relying purely on theoretical models anchored to one-dimensional computational simplifications. The imaging capability is still advancing. New generations of instruments, including upgraded interferometric arrays, are generating surface maps of Betelgeuse with detail that was inconceivable in 1996. Each new image adds data to a picture of the star that is richer and more complete than anything available to previous generations of scientists. And in 2023, those instruments registered something that sent a new wave of attention through the astronomical community. Betelgeuse, which had dimmed dramatically just 3 years before, had now become the brightest it had ever been measured. Chapter 28. Why Betelgeuse Looks Red. The color of Betelgeuse is not decoration, it is data. Every star radiates light across a spectrum of wavelengths, and the shape of that spectrum is determined almost entirely by the surface temperature. Hot stars emit most of their energy at short wavelengths, toward the blue and ultraviolet end of the spectrum. Cool stars emit most of their energy at longer wavelengths, toward the red and infrared end. Betelgeuse glows red because its surface temperature runs around 6,000 degrees Fahrenheit. For context, the surface of our star burns at roughly 10,000 degrees Fahrenheit, which pushes its emission toward yellow-white. The very hottest stars, massive blue supergiants, burn at 50,000 degrees Fahrenheit or more, and their light peaks far into the ultraviolet. Temperature and color map directly onto stellar age and stage. A star begins its life burning hot and often blue or white. As it evolves and expands into a giant or supergiant, the outer layers spread and cool, and the color shifts toward red. Betelgeuse is red because it is old and bloated, a star whose core has already exhausted its hydrogen and helium and is now burning heavier elements, while the outer layers have expanded outward into that vast reddish envelope. The red color also tells you something about the chemistry possible in the outer atmosphere. Cooler stellar surfaces support molecular formation in ways that hotter surfaces cannot. The rich molecular chemistry detected in Betelgeuse's extended atmosphere, the water molecules, the silicon compounds, the complex carbon-bearing species, exists precisely because the outer layers are cool enough to allow molecules to survive against the star's radiation field. There is a subtlety in Betelgeuse's redness that carries additional information. The star is not uniformly red. Different regions of its surface run at different temperatures, and high-resolution spectral maps show patches of cooler and hotter material, corresponding to the positions of giant convective cells. The average color we see from Earth is a blended signal from all those regions simultaneously. What we call Betelgeuse's color is actually the weighted average of a dozen or more convective structures, each with their own temperature profile. This has a direct implication for interpreting the ancient records discussed earlier. If ancient observers described the star as yellower than it appears today, they could be recording a period when the balance of convective cells on the star's visible face happened to show more hot, brighter regions than cool ones, shifting the averaged color. Alternatively, they could be recording a genuine long-term temperature change. Separating these two explanations using historical records alone is currently impossible. What is certain is that Betelgeuse's color today, its redness, is the product of 2.5 million years of nuclear burning that have left the star swollen, cool, and unstable. The red glow is the signature of a star that has used most of what it had, and in 2023, that glow changed in a direction that surprised everyone watching. Chapter 29, The New Brightness Surge of 2023. 3 years after recording its dimmest measurement in over a century, Betelgeuse reached its brightest. In 2023, multiple observatories tracking the star's ongoing recovery from the Great Eruption noticed that Betelgeuse had not merely returned to its pre-dimming brightness levels, it had exceeded them by a significant margin. The star climbed to a brightness level beyond anything in the recorded history of systematic stellar observation, going back roughly 150 years. This was unexpected. The working model after the Great Eruption was that Betelgeuse's pulsation cycle would slowly rebuild itself, the surface would partially recover, and the star would return to something resembling its earlier behavior over a period of years. A return to normal, however disrupted and delayed, was the anticipated trajectory. A brightness surge to record levels was outside the model's predictions. Astronomers responded the way they typically respond to unexpected data. They pointed more instruments at the star, pulled in data from archives to look for analogous historical behavior, and began publishing preliminary analyses as fast as the peer review process would allow. The brightness surge was confirmed across multiple wavelength bands. Optical brightness was at a record high. The infrared signal, which tracks the thermal emission from the star's extended atmosphere, showed corresponding changes. The pulsation cycle, still in its disrupted recovery phase, was producing a particularly bright peak that some researchers connected to the recovery dynamics following the ejection. The surge lasted for an extended period, rather than representing a single sharp peak. Betelgeuse remained at historically elevated brightness levels through much of 2023, before beginning a gradual return toward more typical values. The duration of the elevated brightness added to its significance, ruling out a simple coincidence of pulsation timing. Within the broader research community, this surge became new data in an ongoing argument. Those who had been arguing that Betelgeuse's recent behavior signaled a genuinely unusual evolutionary state pointed to the record brightness as further evidence. A star recovering from an unprecedented eruption should not simultaneously be setting brightness records. Something is driving the star to new extremes in both directions. Those who favored more conservative interpretations noted that the elevated brightness could be explained by the recovery of the pulsation cycle, producing a particularly strong peak, a superposition of recovering rhythms that temporarily added up to a high combined output. Both arguments remained in the literature simultaneously. No consensus formed around the brightness surge as definitively one thing or the other. What the surge did produce was a renewed burst of public attention on Betelgeuse and a corresponding intensification of professional monitoring programs. The star was, by any measure, behaving in ways that demanded close and continuous observation. The question that the brightness surge opened was the same question the dimming had opened 3 years earlier, approached from the opposite direction. Chapter 30. What the brightness surge might mean. 2 readings of the brightness surge exist in the scientific literature, and they lead to very different conclusions about Betelgeuse's status. The first reading is recovery. The Great Eruption disrupted the pulsation cycle by removing surface material. As the photosphere rebuilt itself over the following years, the pulsation dynamics shifted. The recovery of the surface, combined with the natural timing of the longer pulsation cycles, produced a moment where multiple cycles peaked together, delivering a combined brightness higher than any single cycle normally reaches. The record brightness in this reading is the star healing and its overlapping rhythms temporarily synchronizing. The star is stabilizing, not escalating. This reading fits a model where Betelgeuse is still far from its final collapse, and the recent dramatic events, the dimming, the eruption, the broken pulsation, the record brightness, are all variations within the long-term behavior of a turbulent but not yet terminal red supergiant. The second reading is escalation. In certain models of stellar evolution, a red supergiant approaching the final stages of its core burning begins to exhibit increasing amplitude in its surface fluctuations. The outer envelope becomes more sensitive to the changes happening in the core, as the core's energy output shifts with each new burning stage. The star does not settle into a new normal. It oscillates between increasingly extreme states, swinging from record low to record high, with each swing larger than the last. In this reading, the record brightness is not a sign of recovery, it is a sign of growing instability. The same internal processes driving the core toward its final burning stages are producing larger and larger swings in the outer layers. The star is not healing, it is escalating toward an end state. Neither reading is definitively supported over the other by the current data. Both are consistent with the observed brightness record. Both make different predictions about what Betelgeuse's behavior will look like in the coming years and decades, which means continued observation is the only way to distinguish between them. This is the position that observational astronomy often finds itself in. 2 plausible models, 1 data set, and the requirement to wait for more information. What makes the waiting feel less passive in the case of Betelgeuse is the monitoring infrastructure that has been built around the star. The observation of Betelgeuse is no longer something that happens incidentally as part of broader sky surveys. It is a coordinated, sustained scientific effort, involving instruments on multiple continents and in orbit, generating data streams that are actively analyzed by research groups around the world. The sophistication of that monitoring system, and what it would do the moment it detected something definitive, represents one of the more quietly remarkable stories in contemporary astronomy. Chapter 31. How astronomers are monitoring Betelgeuse right now. On any given night, somewhere on Earth, a telescope is pointed at Betelgeuse. The monitoring of this star is continuous, coordinated, and more sophisticated than at any previous point in history. Multiple international programs track its brightness across different wavelength ranges simultaneously, producing data streams that allow researchers to compare measurements made hours apart from different parts of the globe. Amateur astronomers contribute meaningfully to this effort. The American Association of Variable Star Observers maintains a database of brightness estimates of Betelgeuse stretching back over a century, built from observations submitted by tens of thousands of amateur observers worldwide. This historical archive is one of the most valuable resources for understanding long-term trends in the star's behavior. Professional researchers use it constantly. Professional observatories add measurements in the ultraviolet, infrared, and radio wavelength ranges that amateur instruments cannot reach. The Hubble Space Telescope conducts periodic targeted observations of Betelgeuse's ultraviolet chromosphere. Ground-based interferometric arrays provide surface imaging campaigns. Infrared observatories track the thermal emission from the star's surrounding dust and gas. Radio telescopes monitor the molecular emission lines from the outer atmosphere. The neutrino detection network is the most critical component of the warning infrastructure. Facilities including Super Kamiokande in Japan, IceCube at the South Pole, and several other underground detectors contribute to the supernova early warning system. Each facility monitors its detector data in real time and has automated alert systems programmed to fire if the detectors register a burst of neutrino events consistent with a nearby core collapse. The threshold is deliberately sensitive. A false alert is vastly preferable to a missed one. If the alert fires, the signal goes out to observatories worldwide within seconds. Pre-programmed telescope response systems swing instruments toward Orion automatically. Some of the most significant data in the history of astronomy could be captured within minutes of the neutrino burst, before the light from the explosion has even emerged from the star's surface. This system was tested and refined after the 1987 supernova provided a real-world case study. The neutrino detectors of that era were far less sensitive than current instruments, yet they still caught a handful of events. The current global network would be overwhelmed by a Betelgeuse collapse, catching thousands of signals in seconds. Beyond the detection infrastructure, researchers studying Betelgeuse have developed increasingly sophisticated models of what specific pre-supernova signatures to look for in the star's pulsation and spectral behavior. Changes in the ratio of certain molecular emission lines in the outer atmosphere, shifts in the character of the pulsation beyond what has already been observed, unusual brightening or dimming patterns in specific wavelength bands. All of these carry theoretical predictions for what a star in its very final stages might show. Those predictions remain unverified because no red supergiant has ever been comprehensively observed through its terminal phase at close range. Betelgeuse is the closest candidate. Whatever it eventually shows will define what that terminal phase looks like for all future observations of similar stars. The scientists doing this work carry a weight that is unusual, even for a field accustomed to long timescales and distant objects. Chapter 32. The psychological weight on the scientific community. Astronomy is typically practiced on timescales that dwarf human lifetimes. Stars live for millions or billions of years. Galaxies evolve over timescales that make civilization's entire history feel instantaneous. Cosmological processes operate across spans of time so vast they require scientific notation to write down. Astronomers routinely work on objects and questions that will not reach resolution within their careers, or their descendants' careers. The discipline trains people to be comfortable with waiting. Betelgeuse is different. For the first time in the modern era of astrophysics, a significant fraction of professional astronomers believe they may live to see a nearby star die. The combination of Betelgeuse's confirmed proximity to the end of its life, its unusual recent behavior, and its closeness to Earth relative to other supernova candidates has created a situation with no real precedent in scientific history. A team of researchers monitoring a star they expect may explode within their professional lifetimes, and possibly within the lifetime of anyone alive today, is a genuinely novel circumstance. The closest comparison from the past century was the build-up toward the 1987 supernova, but that star gave no warning. Its explosion was discovered after the fact, the light arriving unannounced and only confirmed as a supernova once astronomers looked at archived data and found the progenitor star in old images. For Betelgeuse, the progenitor star is still there, being watched in real time, behaving strangely, generating data, and prompting papers that attempt to estimate timelines carrying uncertainty measured in decades to hundreds of thousands of years. Several researchers who study Betelgeuse have spoken publicly about the peculiar motivation it generates. Knowing they may witness the closest supernova since the invention of modern telescopes shapes how they allocate their time, how they structure their research programs, and how they think about what their careers are for. The urgency is unlike anything most fields of science can produce. At the same time, the psychological uncertainty of not knowing whether the event falls in this decade or in 100,000 years creates its own kind of pressure. The instinct to assign the explosion to a near time frame is strong, partly because the star's recent behavior feels like escalation, and partly because researchers are human beings who want their work to connect to something consequential within a human lifetime. Some scientists explicitly flag this bias in their published work, noting that the desire to witness a transformative event should not be confused with evidence that such an event is imminent. The vigilance required to distinguish between genuine observational signals and the wish to find those signals is a recurring theme in the Betelgeuse literature. What makes the situation singular is that both outcomes, an explosion in a human lifetime and an explosion in a geological timeframe, would be scientifically extraordinary. The monitoring systems built around Betelgeuse will catch the event regardless of when it comes. But the question that sits beneath all the monitoring, beneath all the papers and the instruments and the alert systems, is one that has no current answer and may not have one for a very long time. Chapter 33. The final question that keeps scientists awake. Everything we have covered points toward a single question that sits at the center of Betelgeuse research and resists a clean answer. Will Betelgeuse go quietly, or will it go catastrophically? That question sounds like it is asking about the explosion itself, but the deeper version of it goes further. Will Betelgeuse follow the standard model of a red supergiant core collapse, the kind of supernova that stellar physics has been describing theoretically for decades? Or will it do something that breaks the model the way the Great Eruption broke the model of stellar mass loss? The Great Eruption was a category-creating event. Before it was identified, no stellar model included surface mass ejections as a real phenomenon. Afterward, the models had to be rebuilt to include it. A star that can create a new category of scientific event once is a star that might do so again. The pulsation disruption was also outside the existing models. The record brightness surge was outside the models. Each new piece of Betelgeuse's behavior in the past decade has required some revision to the theoretical framework built to describe it. Scientists who study massive stellar evolution are now asking whether the standard supernova model itself might need revision when applied to a star that has already demonstrated it behaves in ways the models did not anticipate. If the outer envelope of a red supergiant can violently eject pieces of itself before the core collapses, what does that do to the explosion dynamics when the core finally gives way? Does the prior mass ejection change the structure of the surrounding environment through which the shock wave must travel? Does it alter the final mass of the collapsing core in ways that push the outcome toward neutron star or black hole formation? These questions are being worked on now. They were not serious research questions 5 years ago, because the events prompting them had not yet been observed. Betelgeuse has expanded the boundary of what stellar physics must account for. Every surprising observation from the star feeds back into theoretical frameworks that are actively evolving. The star is not just a spectacle. It is a live laboratory forcing science to update itself in real time. What makes the final question so persistent is that its answer will only come once. Betelgeuse will explode, or it will not, within any given human time frame. When the explosion comes, it will either confirm the revised models or break them again. There is no rehearsal. There is no second observation of the same event. Whenever it happens, the data produced in those first hours and days of a Betelgeuse supernova will be the most scientifically rich information ever gathered from a single astronomical event. Every instrument being built, calibrated, and aimed at the sky today carries some fraction of its design priority toward being ready when that light arrives. Every neutrino detector running underground, every infrared telescope in orbit, every radio array spread across a continent is partly a Betelgeuse instrument, waiting. The star sits in Orion tonight, reddish and familiar, pulsing in rhythms that are still recovering from something that had no name before it happened. 700 light years of distance separates us from whatever Betelgeuse actually is right now. 700 years of light travel time separates our sky from the truth. We are watching a recording of a star that may already be dead. And somewhere between that thought and the weight of the instruments watching the sky, the scientists are awake.